Software configuration management. Change in software products. Change is inevitable when computer software is built, and change increases the level of confusion when you and other members of a software team are working on a project. Change in software products. Change is inevitable when computer software is built, and change increases the level of confusion when you and other members of a software team are working on a project. Confusion arises when changes are not analyzed before they are made, recorded before they are implemented, reported to those with a need to know, and or controlled in a manner that will improve quality and reduce error. What is SCM? Software Configuration Management. SCM is an umbrella activity that is applied throughout the software process because change can occur at any time. SCM activities are developed to identify change, control change, ensure that change is being properly implemented, and report changes to others who may have an interest. SCM versus support. It is important to make a clear distinction between software support and software configuration management. Support is a set of software engineering activities that occur after software has been delivered to the customer and put into operation. Software configuration management is a set of tracking and control activities that are initiated when a software engineering project begins and terminates only when the software is taken out of operation. What is an SCI? A software engineering work progresses a hierarchy of software configuration items. SCI is a named element of information that can be as small as a single UML diagram or as large as the complete design document is created. If each SCI simply led to other SCIs, no confusion would result. Unfortunately, another variable enters the process: change. Change may occur at any time for any reason. The first law: no matter where you are in the system life cycle, the system will change, and the desire to change it will persist throughout the life cycle. Bursoff, ETL 1980. What are the changes? Changes in business requirements, changes in technical requirements, changes in user requirements, software models, test code, or for project plan data, other documents. Source of these changes: new business or market conditions dictate changes in product requirements or business rules. New stakeholders needs demand modification of data produced by information systems. Functionality delivered by products or services delivered by a computer based system. Reorganization or business growth. Downsizing causes changes in project priorities or software engineering team structure. Budgetary or scheduling constraints cause a redefinition of the system or product. The software configuration, the pieces, programs, documents, data. Elements of a configuration management system. Component elements: a set of tools coupled within a file management system, for example a database that enables access to and management of each software configuration item. Process elements: a collection of actions and tasks that define an effective approach to change management and related activities for all constituencies involved in the management, engineering, and use of computer software. Construction element: a set of tools that automate the construction of software by ensuring that the proper set of validated components, that is the correct version, have been assembled. Human elements: a set of tools and process features encompassing other CM elements used by the software team to implement effective SCM. Baselines: the IEEE standard number 610.121990 defines a baseline as a specification or product that has been formally reviewed and agreed upon, and that thereafter serves as the basis for further development, and that can be changed only through formal change control procedures. A baseline is a milestone in the development of software that is marked by the delivery of one or more software configuration items and the approval of these SCIs that is obtained through a formal technical review. Baselines. Baselined SCIs and the project database. SCIs: modified software engineering task. SCIs: technical reviews. Approved SCIs: project database. Stored SCIs: baselines, system specification, software requirements, design specifications, source code, test plans, procedures, data, operational system. Extracted SCIs: SCM controls and software engineering tasks. Software configuration objects. Test specification, design specification. Design specification in data design, architectural design, module design, interface design, data model, data design से आया है data model. Module design से component and interface description, algorithm description, PDL. Test specification, component and test specification, source code. The SCM repository. The SCM repository is the set of mechanisms and data structures that allow a software team to manage change in an effective manner. The repository performs or precipitates the following functions: FOR 89: data integrity, information sharing, tool integration, data integration, methodology enforcement, document standardization. Repository content: business content, project management content, model content, documents, V&V content, construction content, business rules, business functions, organization structures, information architecture. Business content: project management content, project estimates, project schedule, SCM requirements, change requests, change reports, SQA requirements, project reports, yeah, audit reports, project metrics, use cases analysis model, scenario based diagrams, flow oriented diagrams, class based diagrams, behavioral diagrams, design model, architectural diagrams, interface diagrams, component level diagrams, technical metrics, construction content, source code, object code, system built instructions, V&V content, test cases, test scripts, test results, quality metrics, documents, project plan, SCM/SQA plan, system specs, requirements specs, design document, test plan and procedure, support documents, user manual. Repository features: versioning saves all these versions to enable effective management of product releases and to permit developers to go back to previous versions. Dependency tracking and change management: the repository manages a wide variety of relationships among the data elements stored in it. Requirements tracing provides the ability to track all the design and construction components and deliverables that result from a specific requirement specification. Configuration management keeps track of a series of configurations representing a specific project milestones or production releases. Version management provides the needed versions, and link management keeps tracks of interdependencies. Audit trails establishes additional information about when, why, and by whom changes are made. The SCM process, the software configuration management process, defines a series of tasks that have four primary objectives: to identify all items that collectively define the software configuration, to manage changes to one or more of these items, to facilitate the construction of different versions of an application, and to ensure that the software quality is maintained as the configuration evolves over time. The SCM process addresses the following questions: how does a software team identify the discrete elements of a software configuration? How does an organization manage the many existing versions of a program and its documentation in a manner that will enable change to be accommodated efficiently? How does an organization control changes before and after software is released to a customer? Who has a responsibility for approving and ranking changes? How can we ensure that changes have been made properly? What mechanism is used to appraise others of changes that are made? The SCM process: SCIs: identification, change control, version control, configuration, auditing, reporting, software, VM.N. Version control: version control combines procedures and tools to manage different versions of configuration objects that are created during the software process. A version control system implements or is directly integrated with four major capabilities: a project database repository that stores all relevant configuration objects, a version management capability that stores all versions of a configuration object or enables any version to be constructed using differences from past versions, a, a make facility that enables the software engineer to collect all relevant configuration objects and construct a specific version of the software, an issue tracking, also called bug tracking capability, that enables the team to record and track the status of all outstanding issues associated with each configuration object. चेंज कंट्रोल, ये इधर और स्टॉप ही है. Change control. For a large software project, uncontrolled change rapidly leads to chaos. For such projects, change control combines human procedures and automated tools to provide a mechanism for the control of change. A change request is submitted and evaluated to assess technical merit, potential side effects, overall impact on other configuration objects and system functions, and the projected cost of the change. The results of the evaluation are presented as a change report, which is used by a change control authority (CCA), a person or group that makes a final decision on the status and priority of the change. An engineering change order (ECO) is generated for each approved change. The ECO describes the change to be made, the constraints that can be respected, and the criteria for review and audit. Change control process one, and a need for change is recognized. Change request from user developer evaluates, change report is generated, change control authority decides, request is queued for action, change request is denied, user is informed. Change control process 2, assign people to SCIs, check out SCIs, make the change, review, audit the change, establish a baseline for testing. Change control process 3, change control process 3, from perform SQA and testing activities, change and check in the changed SCIs, promote SCI for inclusion in next release, rebuild appropriate version, review, audit the change, include all changes in release. Auditing SCIs, change requests, SQA plan, SCM audit. Software configuration audit. How can a software team ensure that the change has been properly implemented? The answer is twofold: technical reviews and the software configuration audit. The technical review focuses on the technical correctness of the configuration object that has been modified. The reviewers assess the SCI to determine consistency with other SCIs, omissions, or potential side effects. A technical review should be conducted for all but the most trivial changes. A software configuration audit complements the technical review by assessing a configuration object for characteristics that are generally not considered during review. Configuration audit questions: has the change specified in the ECO been made? Have any additional modifications been incorporated? Has a technical review been conducted to assess technical correctness? Has the software process been followed, and have software engineering standard been properly applied? Has the change been highlighted in the SCI? Have the change date and change author been specified? Do the attributes of the configuration object reflect the change? Have SCM procedures for noting the change, recording it, and reporting it been followed? Have all related SCIs been properly updated? Status accounting SCIs, change request, change reports, ECOs, status accounting reporting. Configuration status reporting, sometimes called status accounting, is an SCM task that answers the following questions: what happened, who did it, when did it happen, what else will be affected. Configuration status reporting. The flow of information for configuration status reporting (CSR) was illustrated before in change control process. Each time an SCI is assigned new or updated identification, a SCR entry is made. Each time a change is approved by the CCA, that is an ECU is issued, a CSR entry is made. Each time a configuration audit is conducted, the results are reported as part of the CSR task. Output from CSR may be placed in an online database or website so that software developers or support staff can access change information by keyword category. In addition, a CSR report is generated on a regular basis and is intended to keep management and practitioners appraised of important changes. Quality concept. Software quality. In 2005 Computer World, HIL05 lamented that bad software plagues nearly every organization that uses computer, causing lost work hours during computer downtime, lost or corrupted data, missed sales opportunities, high IT support and maintenance costs, and low customer satisfaction. A year later, InfoWorld FOS 06 wrote about the sorry state of software quality, reporting that the quality problem had not gotten any better. Today, software quality remains an issue, but who is to blame? Customers blame developers, arguing that sloppy practices lead to low quality software. Developers blame customers and other stakeholders, arguing that irrational delivery dates and a continuing stream of changes force them to deliver software before it has been fully validated. Quality. The American Heritage Dictionary defines quality as a characteristic or attribute of something. For software, two kinds of quality may be encountered. Quality of design encompasses requirements, specifications, and the design of the system. Quality of conformance is an issue forced primarily on implementation. User satisfaction equal to complement product plus good quality plus delivery within budget and schedule. Quality, a philosophical view. Robert Persig commented on the thing we call quality. Quality, you know what it is, yet you don't know what it is, but that's self contradictory. But some things are better than others, that is, they have more quality. But when you try to say that the quality is apart from the things that have it, it all goes proof. There is nothing to talk about. But if you can't say what quality is, how do you know what it is? And how do you know that it even exists? If no one knows what it is, then for all practical purposes it doesn't exist at all. But for all practical purposes it really does exist. What else are the grades based on? Why else would people pay fortunes for some things and throw others in the trash pile? Obviously, some things are better than others, but what's the betterness? So round and round you go, spinning mental wheels and nowhere finding any place to get traction. What the hell is quality? What is it? Quality, a pragmatic view, a transcendental view, argues like Persig that quality is something that you immediately recognize but cannot explicitly define. The user view sees quality in terms of an end user's specific goals. If a product meets these goals, it exhibits quality. The manufacturer's view defines quality in terms of the special specification of the product. If the product conforms to the spec, it exhibits quality. The product view suggests that quality can be tied to inherent characteristics, for example, functions and features of a product. Finally, the value based view measures quality based on how much a customer is willing to pay for a product. In reality, quality encompasses all of these views and more. Software quality can be defined as an effective software process applied in a manner that creates a useful product that provides measurable value for those who produce it and those who use it. This definition has been adapted from BES 04 and replaces a more manufacturing oriented view presented in earlier editions of this book. Effective software process. An effective software process establishes the infrastructure that supports any effort at building a high quality software product. The management aspects of process creates the checks and balance that help avoid project chaos. A key contributor to poor quality software engineering practices allow the developer to analyze the problem and design a solid solution, both critical to building high quality software. Finally, umbrella activities such as change management and technical reviews have as much to do with quality as any other part of software engineering practice. Useful product. A useful product delivers the content, functions, and features that the end user desires, but as important, it delivers these assets in a reliable, error free way. A, a useful product always satisfies those requirements that have been explicitly stated by stakeholders. In addition, it satisfies a set of implicit requirements, for example, ease of use, that are expected of all high quality software. Adding value. By adding value for both the producer and user of a software product, a high quality software provides benefits for the software organization and the end user community. The software organization gains added value because high quality software requires less maintenance effort, fewer bug fixes, and reduced customer support. The user community gains added value because the application provides a useful capability in a way that expedites some business process. The end result is greater software product revenue, better profitability when an application supports a business process, and or improved availability of information that is crucial crucial for the business. Quality dimensions. David Garvin, GAR87, performance qualities. Thus, the software deliver all content, functions, and features that are specified as part of the requirements model in a way that provides value to the end user. Feature quality. Does the software provide features that surprise and delight the first time end users? Reliability. Does the software deliver all features and capability without failure? Is it available when it is needed? Does it deliver functionality that is error free? Conformance. Does the software conform to local and external software standards that are relevant to the application? Does it conform to de facto design and coding conventions? For example, does the user interface conform to accepted design rules for menu selection or data input? Quality dimensions. Durability. Can the software be maintained, changed, or corrected, debugged without the inadvertent generation of unintended side effects? Will changes cause the error rate or reliability to degrade with time? Serviceability. Can the software be maintained, changed, or corrected, debugged in an acceptably short time period? Can support staff acquire all information they need to make changes or correct defects? Aesthetics. Most of us would agree that an aesthetic entity has a certain elegance or unique flow or an obvious presence that are hard to quantify but evident nonetheless. Perception. In some situations, you have a set of prejudices that will influence your perception of quality. MC calls quality factors: maintainability, flexibility, testability, product revision, product transition, portability, reusability, interoperability, product operation, correctness, reliability, usability, integrity, efficiency. Other views: ISO 9126 quality factors, SCPA section 14.2.3, targeted factors, SCPA section 14.2.4. The software quality dilemma. If you produce a software system that has terrible quality, you lose because no one will want to buy it. If on the other hand you spend infinite time, extremely large effort, and huge sums of money to build the absolutely perfect piece of software, then it's going to take so long to complete that it will be so expensive to produce that you will be out of business anyway. Either you missed the market window or you simply exhausted all your resources. So people in industry try to get to that magical middle ground where the product is good enough not to be rejected right away, such as during evaluation, but also not to objects of so much perfectionism and so much work that it would take too long or cost too much to complete. Good enough software delivers a high quality functions and features that end users desire, but at the same time it delivers other more obscure or specialized functions and features that contain known bugs. Arguments against good enough. It is true that good enough may work in some application domains and for a few major software companies. After all, if a company has a large marketing budget and can convince enough people to buy version 1.0, it has succeeded in locking them in. If you work for a small company, be wary of this philosophy. If you deliver a good enough buggy product, you risk permanent damage to your company's reputation. You never you may never get a chance to deliver version 2.0 because bad buzz may cause your sales to plummet and your company to fold. If you work in a certain application domains, for example real time embedded software application system that is integrated with hardware can be negligent and open your company to expensive litigation. Cost of quality. Prevention costs include quality planning, formal technical reviews, test equipment training. Internal failure costs include rework, repair, failure mode analysis. External failure costs are complaint resolution, product return and replacement, helpline support, warranty work. Cost. The relative costs to find and repair an error or defect increase dramatically as we go from prevention to detection to internal failure to external failure costs. Requirements: design, coding, testing, maintenance. 2000 से 16000. Quality and risk. People get them bet their jobs, their comfort, their safety, their entertainment, their decision, and their very lives on computer software. It better be right. SCPA chapter 1. Example: throughout the month of November 2000, at a hospital in Panama, 28 patients received massive overdoses of gamma rays during treatment for a variety of cancers. In the months that followed, five of these patients died from radiation poisoning, and 15 others developed serious complications. What caused this tragedy? A software package developed by a US company was modified by hospital technicians to compute modified doses of radiation for each patient. Negligence and liability. The story is all too common. A governmental or corporate entity hires a major software developer or consulting company to analyze the requirements and then design and construct a software based system to support some major activity. The system might support a major corporate function, for example pension management, or some governmental function, for example healthcare administration or homeland security. Work begins with the best of intentions on both sides, but by the time the system is delivered, things have gone bad. The system is late, fails to deliver desired features and functions, is error prone, and does not meet with customer approval. Litigation ensues. Quality and security. Gary MC Grau comments WIL05 software security relates entirely and completely to quality. You must think about security, reliability, availability, dependability at the beginning, in the design, architecture, test, and coding phases, all through the software lifecycle processes. Even people aware of the software security problem have focused on late life cycle stuff. The earlier you find the software problem, the better. And there are two kinds of software problems. One is bugs, which are implemented problems. The other is software flaws, architectural problem in the design. People pay too much attention to bugs and not enough to flaws. Achieving software quality. Critical success factors: software engineering methods, project management techniques, quality control, quality assurance. Review techniques. Reviews. There is no particular reason why your friend and colleagues cannot also be your sternest critic. Jerry Weinberg. What are reviews? A meeting conducted by technical people for technical people. A technical assessment of a work product created during the software engineering process. A software quality assurance mechanism. A training ground. What reviews are not? A project summary or progress assessment. A meeting intended solely to impart information. A mechanism for political or personal reprisal. What do we look for? Errors and defects. Error: a quality problem found before the software is released to end users. Defect: a quality problem found only after the software has been released to end users. We make this distinction because errors and defects have very different economic, business, psychological, and human impact. However, the temporal distinction made between errors and defects in this book is not mainstream thinking. A defect amplification model IBM 81 can be used to illustrate the generation and detection of errors during the design and code generation actions of a software process. Errors from previous steps. Error pass through. Amplified errors 1 is to x. Newly generated errors. Defects development step. Defects and detection. Percent efficiency for error detection. Error pass for next step. Pass to next step. Detect amplification. No reviews. Preliminary design 0010 0% 10 6 4. Detailed design 6 4 into 1.5 x equal to 1.5 25 0% 37 10 27 10 27 into 3 x equal to 3 25 20% 94. Code unit test. Preliminary design detailed design code unit test 94 to integration. ये क्या चाहिए 94 integration test blank 00 50% 47 00 validation test 50% 24 system test 00 50% 12 latent errors defect. ये क्या था? Detect amplification. Reviews conducted. क्या था ये? Defect amplification. In the example provided, a software process that does not include reviews yields 94 errors at the beginning of testing and releases 12 latent defects to the field. A software process that does include reviews yields 24 errors at the beginning of testing and releases 3 latent defects to the field. A cost analysis indicates that the process with no reviews cost approximately 3 times more than the process with reviews, taking the cost of correcting the latent defects into account. Metrics. The total review effort and the total number of errors discovered are defined as E review is equal to EP plus EA plus ER. ERR total is equal to ERR minor plus ERR major. Defect density represents the errors found per unit of work product reviewed. Defect density is equal to error total upon WPS, where metrics preparation effort EP, the effort in person hours required to review a work product prior to the actual review meeting. Assessment effort EA, the effort in person hours that is expending during the actual review. Rework effort ER, and the effort in person hours that is dedicated to the correction of those errors uncovered during the review. Work product size WPS, a measure of the size of the work product that has been reviewed, for example the number of UML models or the number of document pages or the number of lines or code. Minor errors found, error minor, the number of errors found that can be categorized as minor, requiring less than some pre-specified effort to correct. Major error found, error major, the number of errors found that can be categorized as major, requiring more than some pre-specified effort to correct. An example one, in past history, if part if past history indicates that the average defect density for a requirement model is 0.6 errors per page and a new requirement model is 32 pages long, a rough estimate suggests that your software team will find about 19 or 20 errors during the review of the document. If you find only 6 errors, you have done an extremely good job in developing the requirements model, or your review approach was not thorough enough. An example 2, an the effort required to correct a minor model error immediately after the review was found to require 4 person hours. The effort required for a major requirement error was found to be 18 person hour. Examining the review data collected, you find that minor errors occur about 6 times more frequently than major errors. Therefore, you can estimate that the average effort to find and correct a requirements error during review is about 6 person hours. Requirements related error uncovered during testing requires an average of 45 person hours to find and correct. Using the averages noted, we get effort saved per error is equal to e testing minus e reviews. 45 minus 6 is equal to 30 person hours per error. Since 22 errors were found during the review of the requirements model, a saving of about 660 person hours of testing effort would be achieved, and that's just for requirements related error. Overall, effort expended with and without reviews. Planning, requirements, design, code, test with inspection, deployment without inspection. ठीक है, with implement deployment time तो with inspection पहले deploy हो गया, without inspection बाद में deploy. Reference model. Planning and preparation, meeting structure, correction and verification, rules, individual play. ये review. Informal reviews. Informal reviews include a simple desk check of a software engineering work product with with a colleague, a casual meeting involving more than two people for the purpose of reviewing a work product, or the review-oriented aspect of peer programming. Peer programming encourages continuous review as a work product design or code is created. The benefit is immediate discovery of errors and better work product quality as a consequence. Formal technical reviews. The objectives of an FTR are to uncover errors in function, logic, and implementation for any representation of the software, to verify that the software under review meets its requirements, to ensure that the software has been represented according to predefined standards, to achieve software that is developed in a uniform manner, to make projects more manageable. The FTR is actually a class of reviews that includes walkthroughs and inspections. The review meeting between 3 and 5 people typically should be involved in the review. Advanced preparation should occur, but should require no more than 2 hours of work for each person. The duration of the review meeting should be less than 2 hours. Focus is on the focused on a work product. For example, a portion of a requirements model or detailed component design, source code for a component. The players, review leader, standard bearer, SQA, producer, reviewer, user representation, REP representative, recorder, maintenance, oracle. The players, producer, the individual who has developed the work product, informs the project leader that the work product is complete and that a review is required. Review leader evaluates the product for readiness, generates copies of product materials and distributes them to 2 or 3 reviewers for advanced preparation. Reviewers Reviewers expected to spend between 1 and 2 hours reviewing the product, making notes, and otherwise becoming familiar with the work. Recorder reviewer who records in writing all important issues raised during the review. Conducting the review the product, not the producer. Set an agenda and maintain it. Limit debate and rebuttal. Enunciate problem areas but don't attempt to solve every problem noted. Take written notes, limit the number of participants, and insist upon advanced preparation. Develop a checklist for each product that is likely to be reviewed. Allocate resources and schedule time for FTRs. Conduct meaningful training for all reviewers. Review your early reviews. Review options matrix. ओके, ये सब क्या है? IPR informal peer review, WT walkthrough, IN inspection, RRR round robin review. Trained leader, IPR no, WT yes, in yes, IN yes, RRR yes. Agenda established, IPR maybe, WT yes, IN yes, RRR yes. Reviewers prepared in advance, IPR maybe, WT yes, IN yes, RRR yes. Producer represents product, IPR maybe, WT yes, IN yes, RRR yes. Producer represents product, IPR maybe, WT yes, IN no, RRR no. Reader represents product, IPR no, WT no, IN yes, RRR no. Recorder takes notes, IPR maybe, WT yes, IN yes, RRR yes. Checklists used to find errors, IPR no, WT no, IN yes, RRR no. Errors categorized as found, IPR no, WT no, IN yes, RRR no. Issues list created, IPR no, WT yes, IN yes, RRR yes. Team must sign off on result, IPR no, WT yes, IN yes, RRR maybe. Sample driven reviews, SDRs attempt to quantify those work products that are primary targets for full FTR. To accomplish this, inspect a fraction AI of each software work product I. Record the number of faults FI found within AI. Develop a gross estimate of the number of faults within work product I by multiplying FI by 1 by AI. Sort the work products in descending order according to the gross estimate of the number of faults in each. Focus available review resources on those work products and have the highest estimated number of faults. Metrics derived from reviews: inspection time per page of documentation, inspection time per KLOC or FP, inspection effort per KLOC or FP, errors uncovered per reviewer hour, errors uncovered per preparation hour, errors uncovered per SE task, that is for example design, number of minor errors, for example typos, number of major errors, for example conformance to requirement, number of errors found during preparation. SQA. Comment on quality. Phil Crosby once said, "The problem of quality management is not what people don't know about it, the problem is what they think they do know." In this regard, quality has much in common with sex. What? Everybody is for it. Under certain conditions, of course. Everybody is for it. Under certain conditions, of course, everyone feels they understand it, even though they would not want to explain it. Everybody thinks execution is only a matter of following natural inclination. After all, we do get alone somehow. And of course, most people feel that problems in these areas are caused by other people. If only they would take the time to do things right. Elements of SQA: standards, reviews and audits, testing, errors, defect testing, defect collection and analysis, change management, education, vendor management, security management, safety, risk management. Role of the SQA Group 1: prepares an SQA plan for the project. The plan identifies evaluation to be performed, audits and reviews to be performed, standards that are applicable to the project, procedures for error reporting and tracking, documents to be produced by the SQA group, amount of feedback provided to the software project team, participants in the development of the software's project, process description. The SQA group reviews the process description for compliance with organizational policy, internal software standards, externally imposed standard, for example ISO 9001 and other parts of the software project plan. Role of the SQA Group 2 reviews software engineering activities to verify compliance with an defined software process, identifies documents and tracks deviations from the process and verifies that corrections have been made. Audits designated software work products to verify compliance with those defined as part of the software process. Reviews selected work products, identifies documents and tracks deviations, verifies that corrections have been made. Periodically reports the result of its work to the project manager, ensures that deviation in software work and work products are documented and handled according to a documented procedure, records any non-compliance and reports to senior management. Non-compliance items are tracked until they are resolved. SQA goals: requirements quality. The completeness and consistency of the requirement model will have a strong influence on the quality of all work products that follow. Design quality: every element of the design model should be assessed by the software team to ensure that it exhibits a high quality and that the design itself conforms to requirements. Code quality: source code and related work products, for example other descriptive information, must conform to local coding standards and exhibit characteristics that will facilitate maintainability. Quality control effectiveness: a software team would apply limited resources in a way that has the highest likelihood of achieving a high quality result. Requirements quality: software quality goals, attributes and metrics. Goal: requirements quality. Attribute: ambiguity. Metric: number of ambiguous modifiers, for example many large human friendly. Completeness: number of TBA TBD. Understandability: number of sections slash subsections. Volatility: number of changes per requirement. Time by activity when change is requested. Traceability: number of requirements not traceable to design or code. Model clarity: number of UML models. Number of descriptive pages per model. Number of UML errors. Design and code quality. Design quality: architectural integrity, existence of architectural model. Component completeness: number of components that trace to architectural model. Complexity of procedural design. Interface complexity: average number of pick to get a typical function or content layout appropriates. Patterns: number of patterns used. Code quality. Complexity, cyclomatic complexity. Maintainability. Design factors, chapter 8. Understandability: percent internal comments, variable naming conventions. Reusability: percent reused components. Documentation. Readability index. QC effectiveness. Resource allocation: staff hour percentage per activity. Completion rate: actual versus budget budgeted completion time. Review effectiveness: see review metrics, chapter 14. Testing effectiveness: number of errors found and critically effort required to correct an error. Origin of error. Statistical SQA: product and process. Collect information on all defects. Find the causes of the defects. Move to provide fixtures for the process measurement. Product and process measurement. And understanding of how to improve quality. A statistical SQA: information about software errors and defects is collected and categorized. An attempt is made to trace each error and defect to its underlying cause, for example non-conformance to a specification, design error, violation of standards, poor communication with the customer. Using the Pareto principle, 80% of the defects can be traced to 20% of all possible causes. Isolate the 20%. The vital few Once the vital few causes have been identified, move to correct the problems that have caused the errors and defects. Six Sigmas of software engineering. The term Six Sigmas is derived from six standard deviations, 3.4 instances defects per million occurrences, implying an extremely high quality standard. The Six Sigma methodology defines three core steps: define customer requirements and deliverables and project goals via well defined methods of customer communication. Measure the existing process and its output to determine current quality performance. Collect defect metrics. Analyze defect metrics and determine the vital few causes. Improve the process of eliminating the root causes of defects. Control the process to ensure that future work does not reintroduce the cause of defects. Software reliability. A simple measure of reliability is mean time between failure, where mean time between failure is equal to mean time to failure plus mean time to repair. The acronyms MTTF and MTTR are mean time to failure and mean time to repair respectively. Software availability is the probability that a program is operating according to requirements at a given point in time and is defined as availability is equal to MTTF upon MTTF plus MTTR into 100%. Software safety is a software quality assurance activity that focuses on the identification and assessment of potential hazards that may affect software negatively and cause an entire system to fail. If hazards can be identified early in the software process, software design features can be specified that will either eliminate or control potential hazards. ISO 9001 is to 2000 standard. ISO 9001 is to 2000 is the quality assurance standard that applies to software engineering. The standard contains 20 requirements that must be present for the effective quality assurance system. The requirements delineated by ISO 9001 is to 2000 address topics such as management responsibility, quality system control review, design control, document and data control, product identification and traceability, process control, inspection and testing, corrective and preventive action, control of quality records, internal quality audits, training, receiving, servicing, and statistical techniques. Testing object oriented applications, testing and object oriented approach. The objective of testing is to find the greatest possible number of errors with a manageable amount of effort applied over a realistic time span. Although this fundamental objective remains unchanged for object oriented software, and the nature of object oriented programs changes both testing strategy and testing tactics. Testing an object-oriented approach, it could be argued that as reusable class libraries grow in size, greater reuse will mitigate the need for heavy testing of object-oriented systems. However, exactly the opposite is true. Each reuse is a new context of uses, and retesting is prudent. It seems likely that more, not less, testing will be needed to obtain high reliability in object oriented system. Testing, to adequately test systems, three things must be done. Definition of testing must be broadened to include error discovery techniques applied to object oriented analysis and design models. The strategy for unit and integration testing must change significantly, and the design of test cases must account for the unique characteristics of software. Testing models, the review of analysis and design models is especially useful because the same semantic constructs, for example, classes, attributes, operations, messages appeared at the analysis, design, and code level. Therefore, a problem in the definition of class attributes that is uncovered during analysis will circumvent side effects that might occur if the problem were not discovered until design or code or even the next iteration of analysis. Testing models, for example, consider a class in which a number of attributes are defined during the first iteration of analysis. An extraneous attribute is appended to the class due to the misunderstanding of the problem domain. Two operations are then specified to manipulate the attribute. A review is conducted and a domain expert points out the problem. By eliminating the extraneous attribute at this stage, the following problems and unnecessary effort may be avoided during analysis. Testing model, special subclasses may have been generated to accommodate the unnecessary attribute or expectations or exceptions to it. Work involved in the creation of the unnecessary subclasses has been avoided. A misinterpretation of the class definition may lead to incorrect or extraneous class relationships. The behavior of the system or its classes may be improperly characterized to accommodate the extraneous attribute. Testing models, if the problem is not uncovered during analysis and propagated further, the following problems would occur and will have been avoided because of the earlier review. During design, improper allocation of the class to subsystem and or tasks may occur during system design. Unnecessary design work may be expended to create the procedural design for the operations that address the extraneous attribute. The messaging model will be incorrect because messages must be designed for the operation that are extraneous. Correctness of models. During analysis and design, semantic correctness must be assessed based on the model's conformance to the real world problem domain. If the model accurately reflects the real world to a level of detail that is appropriate to the stage of development at which the model is reviewed, then it is semantically correct. To determine whether the model does in fact reflect real world requirements, it should be presented to problem domain experts who will examine the class definitions and hierarchy for omission and ambiguity. Class relationships, instance connections are evaluated to determine whether they accurately reflect real world object connections. Consistency of object oriented models. The consistency of object oriented models may be judged by considering the relationships among entities in the world. An inconsistent analysis or design model has representations in one part that are not correctly reflected in other portions of the model. To assess consistency, you should examine each class and its connection to other classes. The class responsibility collaboration CRC model or an object relationship diagram can be used to facilitate this activity. Class model consistency. Revisit the CRC model and the object relationship model. Inspect the description of each CRC index card to determine if a delegated responsibility is part of the collaborator's definition. Invert the connection to ensure that each collaborator that is asked for service is receiving requests from a reasonable source. Using the inverted connections examined in the preceding step, determine whether other classes might be required, or 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 whether responsibilities are properly grouped among the classes. Determine whether widely requested responsibilities might be combined into a single responsibility. Object oriented testing strategies. Unit testing. The concept of the unit changes. The smallest testable unit is the encapsulated class. A single operation can no longer be tested in isolation, the conventional view of unit testing, but rather as part of a class. Integration testing. Thread based testing integrates the set of classes required to respond to one input or event for the system. Use based testing begins the construction of the system by testing those classes called independent classes that use very few, if any, of server classes. After the independent classes are tested, the next layer of classes called dependent classes. Cluster testing defines a cluster of collaborating classes determined by examining the CRC and the object or relationship model. Is exercised by designing test cases that attempt to uncover errors in the collaborations. Or testing strategies. Validation testing. Details of class connections disappear. Draw upon use cases that are part of the requirements model. Conventional black box testing methods can be used to drive validation test. O testing methods. The architecture of object oriented software results in a series of layered subsystems that encapsulate collaborating classes. Each of these system elements, subsystem, and classes perform functions that help to achieve system requirements. It is necessary to test an O system at a variety of different levels in an effort to uncover errors that may occur as class collaborate with one another and subsystems communicate across architectural layers. OT methods. Berard proposes the following approach. Each test case should be uniquely identified and should be explicitly associated with the class to be tested. The purpose of the test should be stated. A list of testing steps should be developed for each test and should contain BR94. A list of specified states for the object that is to be tested. A list of messages and operations that will be exercised as a consequence of the test. A list of exceptions that may occur as the object is tested. A list of external conditions, that is changes in the environment external to the software, that must exist in order to properly conduct the test. Supplementary information that will aid in understanding or implementing the testing methods. Fault based testing. The tester looks for plausible false aspects for the implementation of the system that may result in defects. To determine whether these faults exist, test cases are designed to exercise the design or code. Class testing and the class hierarchy. Inheritance does not obviate the need for thorough testing of all derived classes. In fact, it can actually complicate the testing process. Scenario based test Design scenario based testing concentrates on what the users does, but not what the product does. This means capturing the task via use cases and the user has to perform, then applying them and their variants as tests. Hi, Bhagwan. OOT methods. Random testing. Random testing identifies operation applicable to a class, define constraints on their use, identify a minimum test sequence, and operation sequence that defines the minimum life history of the class object. Generate a variety of random but valid test sequences of exercise other more complex class instances life histories. OOT methods. Partition testing. Partition testing reduces the number of test cases required to test a class in much the same way as equivalence partition for conventional software. So state-based partitioning. Categorize and test operations based on their ability to change the state of a class. Attribute-based partitioning. Categorize and test operations based on the attributes that they use. Category-based partitioning. Categorize and test operations based on the generic function each perform. OOT methods. Interclass testing. Interclass testing. For each client class, use the list of class operator to generate a series of random test sequences. The operators will send messages to other server classes. For each message that is generated, determine the collaborator class and the corresponding operator in the server object. For each operator in the server object that has been invoked by messages sent from the client object, determine the message that it transmits. For each of the messages, determine the next level of operators that are invoked and incorporate these into the test sequence. OOT methods. Interclass testing. Class collaboration diagram for banking application. Card inserted password. ATM user interface. Card inserted password. Deposit, withdraw, account status, terminate, ATM verify status, deposit status, dispense cash, print account state, read card info, get cash amount, ATM verify account, verify pin, verify policy, withdraw requirement, deposit requirement, account info, bank cashier, open account, initial deposit, authorize card, deauthorize, close account, credit limit, account type, balance, withdraw, deposit, close, valid pin, valid account, validation info. OOT methods. Behavior testing. The test to be designed should achieve all state coverage. KIR 94, that is the operation sequences should cause the account class to make transition through all allowable states. Open, empty account, setup account, set the account, setup account, deposit initial, working account, deposit, withdraw, balance, credit account info, withdrawal final, net, non-working account, close, dead account और फिर ये close का symbol. State diagram for the account.